Most applications today, be it cloud services, web servers, or even system software like hypervisors, receive inputs from untrusted sources and act on them. In the case of cloud services and web servers, these inputs could be the client requests that they receive over an open network connection. And in the case of hypervisors, these inputs could be the messages that a hypervisor receives from an untrusted guest operating system. Since these inputs are untrusted, the application must validate that they conform to a pre-decided message format specification before or during processing them. But input validation is a well-known hard problem, so much so that it ranks quite high in the list of most commonly occurring security vulnerabilities in the applications today. Bugs in the input validation code can be catastrophic. They could lead to the applications leaking their sensitive data, such as what happened in the case of the famous Heartbleed bug, or even arbitrary remote code execution attacks leading to a complete takeover of the system. This is where Everparse comes in. Hi, my name is Asim Rastogi. I'm a researcher at the Microsoft Research Lab in India. I'm going to give you a demo of the Everparse tool that me and my collaborators from multiple Microsoft Research Labs and several academic institutions have been working on for the last few years. Everparse is a tool for generating formally proven low-level parser implementations from high-level message format specifications. To use the Everparse tool, the programmer writes their message specifications in a declarative high-level language. For example, the struct sample definition shown on the top right corner of your screen. Given such a format specification as input, Everparse generates formal specifications and low-level parser implementations to parse these messages in a language called F-star. F-star is a programming language and a proof assistant that me and my collaborators work on. Its core is based on a dependent type theory that allows us to prove mathematical theorems about the programs. The F-star code that Everparse emits, containing the formal specifications and low-level parser implementations, is mathematically proven to be safe, functionally correct, and secure. Where safety means that the code is free of any low-level memory errors, such as buffer overflows, use after pre, and null pointer exceptions. It also means that the code is free of any integer arithmetic over and underflows. As I said, the code is also proven to be functionally correct and secure as per its specifications. This proven code is then automatically compiled to safe and efficient C code that can be easily integrated into the existing applications. So from a programmer's perspective, they only specify their message formats in a high-level declarative language, push a button, and out comes low-level parser implementations to parse those messages. Everparse is now being used to parse certain protocol messages in the network virtualization component of Microsoft Hyper-V, the main virtualization technology used in Microsoft Azure. All these messages that may potentially be coming from attacker-controlled sources first go through Everparse produced formally proven parsers, and only valid messages are allowed to go through to the rest of the system. We have also integrated Everparse parsers into verified F-star applications, for example, the record layer of the TLS and QUIC protocols, and even in the DICE secure firmware standard for computing devices. We have blog posts and several papers. Please check them out for more details. In the rest of the demo, I'm going to show you inner workings of the Everparse tool. We'll first look at the basic example that we saw on the couple of slides ago, the struct sample. We'll learn about basics of the Everparse specification language, semantic constraints, parsing actions, and how to integrate Everparse generated code into existing applications. We'll then move on to more interesting examples for doing variable length data, tagged unions, and so on. At the end, we'll put it all together into an interesting and security critical message format. That's the transmission control protocol format. So with that, let's get into the nitty-gritty details of it. We are developing Everparse as an open source project on GitHub. We continue to push releases, and the releases contain both Linux and Windows binary packages. For the purposes of this demo, I have already downloaded a Windows package and extracted it to the Everparse directory. We'll use it for our demo purposes. Now let's look at the basic sample definition that we saw on one of the slides. This sample definition resembles a sample struct definition that you would have written in a C program. However, the fields in this struct are augmented with what are called as semantic constraints. They further constrain what valid sample messages will look like. In this case, the major version is constrained to be exactly equal to 1. The minor version field should have the value 0, and the min field should have the value that is less than or equal to the max field. The entry point qualifier here says that Everparse, this is the place where we expect to integrate existing applications with the Everparse generated code. Now, given such a specification as input, we are going to run the Everparse tool that we have extracted from the Windows package on it. Now, what's happening in the background is that Everparse first generates formal specifications and low-level implementations in the FStar language. It then runs FStar tool on them to formally check that the output code is correct. And once the output code is proven to be correct, it's then going to compile it to C code. Once it's compiled to C code, we'll see how to integrate it. So now Everparse succeeded, and we are now going to see how do we use the output C code into our existing application. So one of the files that Everparse generates is a wrapper file. This wrapper file contains a function called basic check sample. This function takes as input a byte array and length of the array. The function returns true if the byte array contains a valid binary format for sample messages. Otherwise, it returns false. We can simply call this function from our existing C code and use it. For example, I have written a sample client that reads some binary input from a file and then calls the Everparse generated function on it. I have also created two input files, one of them good and one of them bad. The good file contains a valid sample message that satisfies all the constraints that we saw. Its major version is 1, minor version is 0, and the min value is less than or equal to the max value. In addition, there is a bad sample file that violates the constraint on the min and max. Here, as you can see, the min field is greater than the max value. If we run our main driver program on the good sample value, good sample input, we see that the validation succeeds. That is, Everparse has validated the file and it contains a valid binary format for the sample message. However, if we run it on the bad sample input, then the validation fails as expected. Everparse also allows us to register an error handler with us, where we can customize what error behavior we want in the client program. Here, I'm only outputting the struct and the field where the validation fails, and that's what we get. So this is how easy it is. You just write your message specification, input it to Everparse, and then integrate the existing C code using the top-level wrapper function. Now let's see what's actually happening in the background. So we'll see what kind of validation code is actually doing the validation. So here is a C file that is generated from the verified FStar code. This function basic validate sample is the one that is called from the top-level wrapper function that we saw. And this function is the one that's doing the actual validation. As I said, this function is automatically generated from formally proven safe, correct, and secure FStar code. The function first reads a uint32, checks that it satisfies the major version constraint, that its value is equal to 1. It then reads another uint32, checks that it satisfies the minor constraint, that its minor value equals 0. And then it reads min and max and check that the min and max constraint holds. At any point in this time, if the length of the buffer is exhausted in the middle of the validation, this function returns an error. And that error is returned by the top-level function to the application. So we have seen this basic function where we got an input array and validated it for some struct. However, most times, in addition to validation, you also want to read fields out of this binary format. To do that, Everparse provides support for parsing actions. So here is the same sample struct definition, but this time it is parameterized by a mutable uint32 pointer p. And with the field max, we attach what we call as parsing action. This is an on-success parsing action, which means that once the validation of the field max succeeds, once Everparse has validated field max that it satisfies all its constraints, we are going to write its value to the pointer p and return true. Everparse also has support for on-failure actions and several other actions. I refer you to the online manual for more details. Given this specification now, let's see what kind of a wrapper function Everparse generates for this. The wrapper function, as before, takes as input an array and length, but in addition, it also takes as input a uint32 in which it's going to write the max value once the sample message is validated. Now, to use this wrapper function into our driver program, we have another driver program that calls this wrapper function and passes a pointer to a local variable. And if we run this program on the good sample, then we see that validation succeeds, and in addition, the max value is written onto the mutable pointer that we provided. Another mode of using Everparse could be to use it as a guard to reinterpret cast. Note that the sample struct definition that we have been writing can also be specified in the C language. So another application, what it could do is validate the array using the top level function and then immediately do a reinterpret cast. Now this reinterpret cast will cast the buffer into a struct sample star, and then we can operate it as a normal in-memory pointer. So that's another mode of using Everparse, when the input message can have a corresponding representation in the C program. So with this basic example aside, let's now move on to do something interesting. That is variable length arrays and tagged unions. So suppose the format that I want to specify and parse now is as follows. The message that I want to write starts with a length value, uint32, and it's followed by an array of points, and the total length of the array is len bytes, where len is the first field of the structure. Now every point itself starts with a dimension field that's also a uint32, and rest of the point structure depends on what the dimension value is. If the dimension value is 1, then rest of the structure contains just a single uint32 field x. If the dimension value is 2, then rest of the structure contains 2 uint32s x and y. And if the dimension is 3, then rest of the structure contains 3 values x, y, and z. Note that this is truly a variable length structure. Every element of the array can have a different size, and the size depends on the first field of that element on the dimension. To specify this in Everparse, we are going to take it in 2 steps. First, we are going to define a point structure that's a tagged union, and then we are going to wrap it around with an array with a variable length array. So let's first define a point structure. To define point, we first define a 2D point that has 2 uint32s x and y. We then define a 3D point that contains a 2D point and another z field. We then use the case type feature from Everparse to define a type that contains value of one type or the other depending on some contextual tag. And in this case, the tag is provided by the type parameter dimension. So if the dimension is 1, then the point is just a uint32, a single x coordinate. If the dimension is 2, then the point is a 2D point. And if the dimension is 3, then point is a 3D point. Now we can wrap this case type, which is a contextually tagged union, into a structure so that the context is provided by the first field of the struct. So in this definition, the first field is a value dimension. We attach a semantic constraint to it so that its value can either be 1, 2, or 3. And then the rest of the structure is a point that is contextually defined by the dimension value. With this point definition in hand, we'll now see how we can wrap it around into a variable length array. So let me show you the array definition. But before that, note that I'm defining it in a different file, but I do not have to repeat the point definition. Everparse has support for module system, where we can refer to a module in another module and then imports its type definitions. That's what the export keyword here is saying. It's saying that the struct point can be used by other modules who import the point module. Everparse has support for variable length arrays with one contrasting difference from the C language. The length of the arrays in Everparse specifications is specified in terms of number of bytes rather than in terms of number of elements. And the annotation byte size is a sort of a reminder to the programmer so that they can be careful with what they write. So we define a struct point whose first field is length, and the rest of the struct is a points array with byte size len. And this is what we wanted to specify to begin with. So if we go back, this is the message we wanted to specify, and this is the actual message. This is the actual specification for that message. Everparse has several other features. It supports several other imperative actions, as I said. It has support for various other flavors of arrays. It has support for alignments and padding, but I refer you to the online manual for more details. However, the features that we have seen so far are already interesting enough that we can do realistic and security critical formats such as the transmission control protocol. TCP protocol is one of the protocols in the Internet Protocol Suite, and it underlies most of the communication. And you name it, and the communication depends on TCP. The TCP is a decades-old protocol. RFC 793 and others define what a TCP message looks like. It's a variable length format because the TCP options and padding can have variable length, and they can be completely absent as well. To help parse this message, a TCP message contains a field called data offset that represents the offset of beginning of the data from the beginning of the message. And using this, clients can parse a TCP message. As I said, TCP protocol has been around for decades. Its implementation in software like Linux kernel has also been around for more than a decade. However, parsing such variable length formats is so hard that even as late as 2019, Linux kernel has been fixing out of bounds exceptions when parsing TCP options. So here is a bug that was fixed in 2019 that accesses options, and it accesses options again without making sure that it's not overflowing. Whereas in Everparse, if we can specify these TCP options, we get mathematical proofs that there is no such error in the output emitted C code. So using a similar structure as points array, we can define TCP also in Everparse, and the whole specification takes about 180 lines of code. This specification can now be given as input to the Everparse tool, and out comes a verified low-level implementation for parsing TCP messages that is provably free of such bugs. So that finishes my demo. There is a lot that has been keeping us busy in this space. We are adding more and more features to Everparse, including support for streams, support for more expressible actions, verifying actions themselves, error handling, and so on. We are also looking at applying Everparse to more security critical applications such as ASN.1, X.509 certificate. We have sample message format specifications for many of the internet protocols. We are looking into integrating them and see how they perform, and so on. As I said, Everparse is open source. Give it a spin and get in touch. We would love to hear from you. Thank you.